The magnetic properties of solids. Chapter 10, Magnetic Properties. Okay, two different magnetism. One is induced magnetism, and this is the material which shows a magnetic only when the external magnetic field exists. Like example, diamagnetism and paramagnetism are good examples for this. And another type of magnetism is spontaneous magnetism. Once it is magnetized, the material shows the magnetism even without the external magnetic field, and that is ferromagnetism and ferrimagnetism and anti-ferromagnetism and things like this. Okay. So we are going to have two different magnetism just like this, and we are going to discuss about each magnetism in this class. Okay. And then we have two different magnetic material. The well-known one of this type is a well-known the soft magnet and hard magnet. Soft magnet is easily magnetized and easily demagnetized material, like silicon ferrite and Fe nickel and so forth. And we use this for the magnetic information storage, like tape and things like that. Okay, and then a hard magnet, of course, it is difficult to magnetize the material, and once it is magnetized, it is difficult to demagnetize the material. So the example is Optical. This is a well-known hard magnet, Optical, and then other ferrites. And as we are going to talk about the origin of magnetic moment. We have two sources for the electronic magnetic moment, and one is the orbital motion of electrons. That is a good source for the magnetic moment of the material. And then another one is the intrinsic angular intrinsic electron angular momentum. We call this a spin angular momentum, okay? So as you can see, the electron which is orbiting the nucleus, and this electron not only orbiting around the nucleus, but also it just have the rotation, spin itself. So these two motion of electrons will give you the magnetic moment, okay? And magnet kinds of magnetism. Let me write down this thing and then this board here. Kinds of magnetism, okay, which is going to be discussed in this class, and that is dia. Number one is the dia magnetism, and number two is the para magnetism, and then number three is the ferro magnetism and anti-ferro magnetism, and then number four is the ferri magnetism. Okay, we are going to discuss about this four, and all this magnetism come from two sources of electron actions. One is the orbiting action, and the other is the spinning actions of electrons. So let me discuss about the diamagnetism first. And dia and the para is induced magnetism, induced, and these are the spontaneous magnetism. Okay. And first, if you want to talk about the diamagnetism, you can see that the orbiting action of electrons will give rise to the current, okay? I'm sorry. It give rise to the orbiting electron itself is a kind of a current, a change in the electric field, something like that, which will induce the magnetic moment, okay, by Maxwell equation, the third Maxwell equation. And this magnetic moment, which comes from this inherent electrons orbiting action, will give rise to the current, okay? And then again, this current will give rise to the magnetic moment. Magnetic moment. So the diamagnetism is naturally it's a kind of a negative susceptibility. Okay, magnetic field. Chi H, and this chi value is negative because it's coming from the inherent electric orbiting motions through this reaction. And you can look into the text, the details of this, and then you'll find that this magnetic susceptibility of diamagnetism is going to be minus. It has a minus sign here, and ZQ square and then R square. This R is the radius of the orbiting electrons. So this R square is mean square distance of electrons to nucleus. You can see that, right? So if you have a heavy atom, like a bismuth, something like that, which has a big radius R, it inherently going to have a high susceptibility for this diamagnetism. And if you look into the paramagnetism, we can distinguish two cases for this. And then the first one was the metal. We have discussed about this metal case, the free electron paramagnetism, right? And the non-metal case, we can distinguish these two. And in the metal, we are going to talk about the free electron paramagnetism. And then we have discussed about this, and we got a conclusion that the magnetic susceptibility for the chi in a metal system is not a function of temperature. That is a very, very important thing, right? But in non-metal case, all you have to do is you are going to find the number of spins in a system. And we have to talk about the unpaired bound electrons in this case. Okay? And then in this case, the chi para is, of course, it's a function of temperature, such that it's inversely proportional to the temperature. Okay. So the paramagnetic materials, if you apply the electric field, magnetic field, then it is going to be magnetized by this paramagnetism. But if you increase the temperature, then the magnetic moment is going to diminish. It's going to be disappear finally at the high temperatures. So if you make a device in a paramagnetic materials, then at first you're going to have magnetized materials with the external magnetic field, but that magnetic field will create the current in itself. We call it eddy current. Okay? That current will going to heat up the material. And then the material, as it is magnetized, the material becomes, the temperature of the material is going to increase, so that finally the magnetic moment decreases with the time. Okay? That's what usually happens in the paramagnetic materials. So every material we're going to have diamagnetism and paramagnetism in itself because it is inherent properties. So in total chi susceptibility is going to be chi dia and chi para by free electron and plus chi para with the unpaired electrons. If the system has all of this, then the total magnetic susceptibility should be added, just like this. And some of the materials, these are trivial, and then this is the this total susceptibility can be approximated to the diamagnetic susceptibility, and we call that material in that case diamagnetic materials. Okay, and then some of the materials, especially the metal, this chi para is big compared to the dia and the para unpaired electrons. Then that happens especially in the metal case, and then this paramagnetic susceptibility is most important, and other things can be ignored. In a non-metallic case, the unpaired electrons are going to tell the magnetism of the material. Okay? So if you draw the magnetic moment and the magnetic field so that the slope is going to be susceptibility of the materials, then this slope is going to be para, that is a positive, and the negative is the dia. And y scale is almost the same. Okay? I think dia is more or less than the para, so we have to, if you draw in the same sense, we have to draw something like this. Okay? Dia is negative and para is the positive. Now let's move to the ferromagnetism. If you want to understand the ferromagnetic magnetism, then you have to get a concept, ferromagnetism. You have to think about the exchange energy. That is just a terminology that has to be used to explain why material has a spontaneous magnetization, things like that, okay? That is a very weird phenomenon, as a matter of fact. Spontaneous magnetization. Spontaneous magnetization. This exchange energy is the energy related to the interaction between the nearest spins, okay? And in a ferromagnetism, the materials which shows a ferromagnetism, this spin direction is parallel. Then the exchange energy of the system becomes the lowest. Okay? Then in that sense, we are going to create a new terminology, exchange energy. And in the ferromagnetic materials, the spins nearest neighbors, between the nearest neighbors, they want to align themselves in parallel to lower the system energies. In other words, the exchange energies of the system. In that case, we're going to call this material is a ferromagnetic material. But if this exchange energy is lowest when the nearest neighbors is anti-parallel, we do have this, and then this is going to be called anti-ferromagnetic materials. We don't know why ferromagnetic materials has the lowest exchange energy when the nearest neighbors spins are aligned parallel, and anti-ferromagnetic materials, it has the lowest exchange energy when the nearest neighbor spins in the anti-parallel. We don't know the reason for that. We just simply know that if we assume that the ferromagnetic materials should have the exchange energy lowest when the nearest neighbor spins are parallel, then we can explain the ferromagnetic nature of the materials. And the exchange, we just assume that the nearest neighbor spins is anti-parallel, should render the lowest exchange energies in the ferromagnetic, in the anti-ferromagnetic materials. Then we can explain the nature of anti-ferromagnetisms of that materials. Okay, so we just got a postulation on this. We do not have any theoretical background on this. Then you naturally say, wow, if the in a ferromagnetic materials, if they want to align themselves in one direction, then we are going to have a very big magnetic moment, right? So if that is the spontaneous reaction, then as the times go by, this ferromagnetic materials, the magnetic moment of this ferromagnetic materials becomes large and large and large forever, so that it's going to show very big magnetic moment every ferromagnetic materials. And it does not happen in the real world. What happened is that it does have a magnetic domains. Okay? Like a polycrystal. Polycrystal grain boundaries. So in a certain range, the spins want to align these directions in a ferromagnetic materials to lower their exchange energies, but it's not going to extend it forever to the next domain. And one domain is going to align this way, and then the other one is going to align this way, and then the other domain is going to be aligned this way. And inside this domain, of course, the exchange energy is the lowest when the spins are nearest neighbors has a parallel direction of their spins. But it's not going to extend forever. Just like the polycrystal in the crystal structure, we call that the difference between the single crystal and the polycrystal is that the polycrystal inside the grains, it does have a single crystal nature, but that orientation of the atomic arrangement is not going to be extended to the next grain boundary. It's just the same concept. And we are going to talk about this in the final class on the 11th, next Monday, okay? So here, let me just explain the ferromagnetic magnetisms of the materials. It goes this way. For example, if you have an iron has 26 electrons, okay, and then it does have 1s2, 2s2, 2p6, okay, and then next 3s2, 3p6, 3d2, and 4s2. You guys all know this, Hund rule and something like that. And then if you draw in the D shell, you are going to have 1, 2, 3, 4, 5 orbit. And then the first one, it is paired. And then from the next one, it is a single. It's not paired. So all these, before this D shell, like S, 3s6, and inner shells, all paired. The electrons are all paired. So we have 4 unpaired electrons, and then the magnetic ferromagnetic moment of this is going to be 4 times Bohr magneton, the unit of the magnetic moment, right? But because of the structure effect, this it should be theoretically for Bohr magneton. Is the measure we measure, and then it turned out it is decreased to 2.2, and that's just for the structural effect. Okay, so basically this theory is okay. The unpaired electrons will show the spontaneous magnetism, so that the magnetic moment of ferromagnetic materials is just proportional to the number of unpaired electrons. That's what has been postulated, and that is very close to what's happening in the real world. Okay? That is a good way to explain this. And other things you can do the same token, chromes and manganese and things like that. Okay? And then we do have a Curie temperature, things like that. But the Curie temperature is the temperature which the spontaneous magnetism disappear. So above that, the Curie temperature, the materials is going to work like paramagnetic materials. Below the Curie temperature, if the material is a ferromagnetic material, then it shows the ferromagnetic properties. So that we should remember there exists the Curie temperature, and in this case, the magnetic moment is the number of unpaired electrons, and then hyperbolic tangent things like that over kT. The temperature dependence of this over kT. And then you can deduce the this equation in the text. Okay, we are not going to go to details of this, but it is related to the unpaired electrons. And anti-ferromagnetic magnetism, anti-ferromagnetism it's just the opposite concept of the ferromagnetic materials. And we have a Curie temperature for the ferromagnetic materials, and we have a new temperature for the ferromagnetic materials, anti-ferromagnetic materials, new temperature. And this is the temperature above which no anti-ferromagnetism can show. Okay, so above this temperature, the material becomes paramagnetic. All right. The final interesting magnetism is this ferrimagnetic materials. Ferrimagnetism. Well, in the ferrimagnetic materials, some spins shows a spontaneous line up, parallel line up, okay, like a ferromagnetism. And some spins do show the anti-ferromagnetism and nature. Okay, so this ferrimagnetism, the materials which shows the ferrimagnetism, some of the spins in the unpaired electrons show the ferromagnetic nature, which means the exchange energy becomes low as their spin direction is parallel, and other spins in the same material, they show the anti-ferromagnetic nature. And the this is a very important in the real in the practice. And the ferrimagnetic, most of the ferrimagnetic materials has a spinel structure. We call that a spinel structure. And then that is metal, oxygen, and for example, Fe2O3 base materials. It has a structure, something like that, okay? And in this case, Fe2O3, 5 d shells electrons is going to compensate to show zero magnetic moment. So actually this one does not have any net magnetic moment because all are they paired, okay? And then the important thing is this MO structures. And for this M, we are going to have divalent metals. Sorry. For example, the manganese is a 23, Fe24, and CO 25, and nickel 26, copper 27, and zinc 28. Okay? And then this one has a 5 Bohr magnetons, has a net magnetic moment. And this one has a 4, 3, 2, 1, 0 magnetic moment. And this is perfectly matched with the concept that we had for the ferromagnetic materials, things like that, okay? And this oxygen is going to work with this divalent metal ions to make the whole system as a ferromagnetic material. And the ferromagnetic material, why ferromagnetic material is important? The ferromagnetic material is in itself, it's an insulator. Okay? So that as it is magnetized, no current is going to flow inside the materials, so no heating up by Joule heating. So the temperature is not going to be raised with the magnetization. And that is very important because in the ferromagnetic materials, it has a Curie temperature. So that's why this ferromagnetic material is industrially important. Ferromagnetic materials is almost a metal all the time. So it has a huge current and it becomes very, very hot as it is magnetized and then long time use. So industrially speaking, the ferromagnetic except the special cases, the ferromagnetic material is important because it is an insulator. There is no heating up. So that is very important. And in the spinel structure, we are going to have two cases for this. One is, what time is it? Who has the time? Okay. We are going to have spinel structures and inverted spinel structures, and those structures are very closely related to the magnetic moment of this ferromagnetic materials. So in the next Monday, in a final lecture, you're going to have a final lecture on the next Monday, right? In the final lecture, we're going to discuss about the crystal structure a little bit, and then we want to discuss why the ferromagnetic materials, the magnetic moment of ferromagnetic materials, which shows a spontaneous magnetization, does not increase its magnetic moment forever. Why there is no magnetic moment in a ferromagnetic materials in the real practice before magnetization of the ferromagnetic materials. And in order to explain that, we have to introduce a concept, a domain, magnetic domain. And then we're going to talk about the magnetic domain in the last lecture. And then wrap up the whole class of this second semester of 2017. Okay? Any questions for the exam? No. Good. I'll see you on a Monday then.